Chromatic aberration is a popular effect with digital images, perhaps as an exaggeration of trying to mimic how analog images used to look. But it's also happening within the eye, giving important cues of distance, guiding our focus to have a clear image. And there are, of course, many reasons why it is harder for us to focus clearly on the RGB display image of a digital screen relative to a naturally lit object. But the differences between these situations regarding chromatic aberration in the eye are one of the factors behind this. So that's what I'm going to cover here, why there is such a difference and how it matters for vision. Light refracts at the border between two optical media of different densities, and this is how a magnifying glass or the lens in the eye works. And of course, this is how the image is focused onto the retina. However, this process also depends on the wavelength of light. And so, since short wavelength light bends or refracts more at the border between these two optical media, and there can be several layers of this as in the eye. In the eye, short wavelength light, so violet and blue, are focused slightly more towards the front of the eye relative to long wavelength visible light like orange and red, which are focused more towards the back of the eye. And of course, this whole rainbow of separated frequencies or colors of light within the eye can be moved back and forth. That's what the lens is doing to focus the image. Now, with natural light, there's always the full spectrum present, which means that as long as accommodation, which is this process of adjusting the lens for clear focus, works more or less correctly, then some part of the spectrum will always be in perfect focus, while other parts further away from the spectrum regarding chromatic aberration will be gradually more out of focus. Not so with an RGB image. Here, the visual system is presented with an unnatural challenge to which it can react in two ways. One is that it focuses on one of the three primaries, but then the other two will be quite out of focus. The other is that it focuses somewhere between two of them, but then all of these three components will be out of focus. And again, this is in contrast to how it works in natural light, where at least some part of the spectrum will always be in perfect focus. There have only been a handful of studies on this question, and they show in general that indeed broad bandwidth light makes it easier and more efficient for the visual system to focus on an image. And this we can see from greater gain and lower phase lag with wide spectral bandwidth stimulation relative to narrow band, let's say RGB spectra. They also show that spectral bandwidths matter more for dynamic situation, and this is particularly interesting when it comes to AR goggles or helmet-mounted displays, where the use is such that the viewer has to focus on the display which is close to the eye and then focus on some object that is farther away. So it's a dynamic situation which can confuse the accommodation response more because of the narrowband RGB spectrum of the display. And finally, they also show that short wavelength light is particularly problematic in this regard. And that is, first of all, because chromatic aberration is not a linear function. So relative to, let's say, the center of the spectrum, blue light requires a greater compensation for chromatic aberration than red light. And this difference can be even greater than 1 diopter, so it's quite significant. On top of that, in the foveola, which is the very center of the retina responsible for sharp vision, S cones are basically absent, and these are the receptors which detect short wavelength blue light, and so by default, acuity for narrowband short wavelength light is already lower, Plus, blue light also scatters more within the eye, further reducing acuity. And so, because of these, we see an over-accommodation response for wavelengths below 430 nanometers, and a greater lag and more micro fluctuations in the accommodation reaction. So the visual system tries to compensate. It can compensate to a great degree, but not completely. And so to sum it up, there are effects of spectral bandwidths on ocular accommodation and on visual acuity, and the negative effects of narrow bandwidth stimuli are greater when the proportion of blue light is bigger and when there's a dynamic situation in viewing. And one interesting open question here, on which I haven't seen much research, is whether these processes may contribute to the temporary myopia that many people experience with prolonged digital display use, because the cues behind them through longitudinal chromatic aberration are very similar to how myopia is formed in childhood. I'll do a separate video on that one. But here I just wanted to mention that there might be a connection, because mechanistically it seems to be a very similar scenario, just on a different time scale, and I haven't seen any studies on this. And further, from what I have just shown here, based on a handful of studies, there seems to be a definite visual advantage to using a broader spectrum, even in RGB digital images. And that is not the direction in which the industry has been going for many, many years and is still going, where most displays are using ever narrower spectra to increase the gamut, so basically to increase the number of colors that can be displayed. And these colors will also be more vivid looking, more salient and more saturated, which is attractive at first sight, but it also has some other negative effects aside from what I have discussed here regarding chromatic aberration. They also have some negative adaptation after effects in the long term, which I will again cover in a separate video. But the solution to all of these problems would be to use a broader spectrum, more natural light, ideally daylight. And that is what we are doing with PicSun. We are bringing daylight directly into the display. And the references that I used here, you can find in the video description, but also you can find them and many, many more articles in related topics on PicSun's references page, with my short bullet point summaries as well. So if you're interested in the topic, check out that one, and thank you for your attention.